Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at a few problems from Unit 2 and 3, which cover kinematics in one dimension, as well as kinematics in two dimensions, which we've been calling projectile motion. These problems are going to be coming from your test number 2 review, which there are copies of that on Canvas, which you can access. But here we're going to be doing a little bit of review on how to set up and solve a medium-level kinematics problem involving motion in two directions. Specifically, we're going to be looking at problems number 3 and 4 on your review for test number 2. I will read them for you and then we will get started. So our problem says this. Suppose you are playing catch with a friend on one Saturday afternoon. You throw the ball to him and at an angle of 35 degrees above the horizontal with a velocity of 15 meters per second. So before we finish out, let's go ahead and get a picture going now that we have a little bit of an idea of what we're doing. So we are playing catch with a friend. So roughly here we are. Happy to be out here. I guess my legs should be touching the ground probably. And then we've got a friend over here. We are playing catch and we are just tossing a ball back and forth and between us. It does say we throw the ball with a velocity of 15 meters per second. So we'll say that we launch our object. Our initial velocity, we'll go here, is 15 meters per second at an angle. We're going with 35 degrees above the horizontal. That just means 35 degrees relative to the ground, effectively. It says, if your friend catches the ball standing still, assume he is on level ground at approximately your height, how far away must they be standing? So the idea with our friend is that they're going to catch the ball at about the same height that we are throwing the ball from. They're about the same height as we are. We're on flat ground. And that will be important as we go through setting up and solving our problem. So the question is, how far away must they be standing? So from where I am located to where my friend is located, we're looking for how far away they must be standing, which is essentially our delta x value here. So in order to set up and solve our problem, we first need to take into account what we know and what we don't know. So I'm going to come to a new page and just list out the variables that we've been dealing with for kinematics and projectile motion. So delta x, initial velocity in the x direction, final velocity in the x direction, acceleration and time. And because we have an object that's moving in more than one direction, we also want to list out our variables in the y direction to keep track of what's going on here. So delta y, initial velocity in the y, final velocity in the y, acceleration in the y, and time. Now for any projectile motion scenario, we are going to assume air resistance is negligible, meaning we will not be accounting for its effect, which allows us to assume acceleration in the x direction is 0 meters per second squared. For the y direction, we will assume only gravity is acting on our object in the y direction, so our acceleration will be negative 9.81 meters per second squared. Negative because gravity does want to cause objects to accelerate toward the ground. So regardless of the other values that we might know, we can always assume those to be true if we are on Earth, and we assume to ignore air resistance. So I'll come back to my picture. I'm given a little bit of information here, specifically about my velocities. So I will start there. 15 meters per second at an angle of 35 degrees. Now if you'll notice, that 15 meters per second doesn't line up perfectly with the x direction or the y direction, which means we need to take that 15 meters per second and break it down into its components so we can see what's happening horizontally as well as vertically. So I'm going to redraw my velocity vector down here a little bit larger so we can get a better idea of what we're working with. 15 meters per second at an angle of 35 degrees. So what I will do here is I'm going to go ahead and draw the components of my velocity vector, initial velocity in the x direction, and initial velocity in the y direction. And we want to solve for both of those. So for the x direction, that is adjacent to my angle, remember our trig functions here are going to come into play because we are dealing with a right triangle. So I'll first break down and to find my initial velocity in the x direction. So that is adjacent to my angle with the hypotenuse. So we'll set something up, a function that looks like this. Cosine of our angle, 35 degrees, is equal to my adjacent side, which here is my initial velocity in the x, divided by my hypotenuse, which is 15. To get my initial velocity in the x direction, I'm just going to multiply by 15 on both sides of my equation. So 15 divided by 15, those values will cancel out. And we'll now have an expression to find our initial velocity in the x. That would be 15, which is a velocity, times cosine of 35 degrees. So now I'll plug those values in, making sure I'm in degree mode. 15 cosine of 35 degrees. Oh, got to switch my mode there. 15 cosine of 35 gives me a value of about 12.3 meters per second. We will round that to 3 significant figures. Again, our value here should be less than 15 because it's one of our components and not the resultant velocity. Okay? So now we have one of our values, initial velocity in the x, and now we'll do the same thing for the y direction, except we need a different trig function. The y component is opposite of my angle, along with the hypotenuse that we know, so here we will use a sine function. So we'll set up an equation that looks like this. Sine of our angle, 35 degrees, is equal to initial velocity in the y, which is opposite of our angle, directly across, divided by our hypotenuse, 15. So now we will multiply by 15 on both sides of our equation, because we want to solve for initial velocity in the y. So 15 over 15, those will cancel out, which will leave just the variable that we're looking for by itself. And we'll have an expression that looks like this. Initial velocity in the y direction is equal to 15 sine of 35 degrees. So again, something very similar to what we already solved for, just a different trig function because we want a different component here. So 15 sine 35 is 8.60 meters per second. And again, our value here should be lower than 15 because it's one of our components, not the resultant. And it should also probably be lower than our x component because our angle here is under 45 degrees, which means more of our velocity will be horizontal than vertical. So now we're just going to take our values and plug them back into our list of variables. So our initial velocity in the x we solved to be 12.3 meters per second, and our initial velocity in the y, 8.60 meters per second. Now, because our acceleration in the x direction is 0, that means our object isn't going to speed up or slow down, aka change its velocity in the x direction. So we can pretty much assume our velocity the whole time in the horizontal direction is 12.3. So we want to find delta x, how far away our friend is standing. But we actually don't know enough information. Even though it kind of looks like we do in the x direction, we actually need time to be able to get to our final answer. However, it doesn't seem like we have enough information in the y direction to help us get there. So if I come back to my picture, I have to think about some of the other variables I might know. I still don't know time. My final velocity, I'm not really sure about exactly what it's doing in the y direction when it reaches my friend. But what about our heights? We're told here that our friend is about our same height. We're standing on flat ground, which means whatever height we're throwing the ball from, we can assume it's being caught at the same height. We don't really know what this height is, right? We just know that it's about the same value as our ending height. We could say it's 1.5 meters, which would mean we would end at 1.5 meters, right? We don't actually know what those values are, but we're given enough information to know that they are the same. which means our delta y here, the difference between our ending height and our beginning height, is 0. That does not mean, as we've talked about, that the ball never travels up. It just means that our ending height is equivalent to our starting height. So here, our delta y is 0 meters. And that's one of the missing clues here in order to solve for the time value in the y direction. So now, we don't really know v1 in the y direction, nor are we terribly concerned about it. So what we can do here is assume that we don't know that value, look at our kinematic equations. That should tell us we're going to use equation number 2. So I'm going to write that out. Delta y is equal to initial velocity in the y direction times time plus 1/2 acceleration in the y times t squared. So we just list out equation 2 because we're missing v1 in the y direction. So now delta y is 0 meters. Our object starts and ends at the same height, is equal to initial velocity in the y, which we determined to be 8.60 meters per second, times t, plus 1/2 multiplied by our acceleration in the y direction, negative 9.81 meters per second squared, multiplied by t squared, which we are looking for here. So now we'll multiply through anything that we can and simplify our equation down. So 0, nothing we can do with that, we'll leave it at 0. We're going to take the units out so we can just deal with the numerical values here. 8.6 times t just gives me 8.6t. 1/2 times negative 9.81 gives me negative 4.905 t squared. Now, as we talked about in class, there are a few ways we can go about solving this problem. And because we have a t and a t squared variable, what we can do here is we could just factor out a t variable from both parts of our equation here. And we could also move one of our values to the other side of our equation and then divide by t because we have a t variable in both parts of our equation. Really, either one is an appropriate way of solving this. So what we've done in class is we've said 0 is equal to t, which we can factor out because we have a t on kind of in both parts of our equation on the right, is equal to 8.6 because I'm pulling out one of those t variables, is equal to 4.905 multiplied by t. And then we can simply take what is inside of our parentheses and set that equal to 0. Because essentially what we can do here is we can divide out t now on both sides of our equation, which means 0 over our time is just going to be a value of 0. Okay? We know that time will not be 0 because, well, time describes how long our object's moving, which will not be a 0 value. So we won't have an undefined answer here. So now we'll have 0 is equal to 8.6 minus 4.905 times t. And then we can, well, let's say add 4.905t to the other side of our equation. So now we have something that looks like this. 4.905t is equal to 8.6. And then finally, to get t by itself, we can divide by 4.905 on both sides of our equation. Oh, excuse me. Click there. So 4.905 divided by 4.905, those values will cancel out, leaving t by itself, which is what we want. And we'll plug in 8.6 divided by 4.905, and we get a time value of about 1.75 seconds. So here t is equal to 1.75 seconds. Our time value, again, should be positive because it's a scalar. So if we do end up getting a value that's negative, go back through some of your work and check to see if you didn't account for a negative earlier on. So now that we have time, we can come back to our list of variables and plug this in. 1.75 seconds. 1.75 seconds. So we are now mostly done with our problem, except we need to find delta x. As we've talked about in class, equation 2 is usually the best equation to use because our acceleration is 0, which can simplify our equation down. So now we'll write out equation number 2 for the x direction. Delta x is equal to initial velocity in the x direction times time, plus 1/2 acceleration in the x times t squared. So if we plug in a 0 value for acceleration in the x, 1/2 times 0 times t squared, that is going to give us a value of 0 because we have a 0 multiplied through in that part of our equation. That's going to leave just this small chunk of our equation to work with, which is actually a pretty easy part to work with comparatively. So delta x is equal to our initial velocity in the x, which we determined with the trig function to be 12.3, multiplied by the time value that we just solved for, 1.75 seconds. So we will multiply those values together, and we end up getting a delta x of about 21.56, round that up to 21.6 meters. So if we were throwing the ball with our friend under these conditions, they would need to be standing approximately 21.6 meters away. So again, when we are dealing with projectile motion scenarios, we always start by drawing a picture, give us a context of what's going on, listing out our variables so we know what information we have, and then beginning the process to solve for our final answer. Usually that might involve a few other steps. Here, we had to break our velocity down into its components, figure out a time value, even though we weren't directly asked for a time value, and then use that time value as a way to get to our final answer. So remember, even though we might be looking for one final answer, that doesn't mean that is the only thing we're going to need to find along the way. Now, question 4 says this: from the information provided in this previous problem, determine the height of the ball at the peak or highest point of its trajectory. So if we look back at our picture, what we are looking for now is, what is the height of the ball at the peak of its trajectory, right? What is this value? We'll call that h. We could also call that, delta y, for example. Okay, but now we want to figure out how high does the ball travel at the peak of its trajectory. Now, a lot of the information we found is going to apply to question 4, but some of it's going to change. So what I'm going to do now is this. For number 4, I'm just going to list out some variables and see what we're going to keep from problem 3 and what we're going to maybe now need to reevaluate for problem 4. So delta x, here's what we have to see. Delta x is actually, from our last problem, 21.6. That's the entire length from where I'm standing to where my friend is standing. When I'm at the peak of my trajectory, I'm not a full 21.6, or the ball is not, we should say, a full 21.6 meters away from where it begins. So we can't just take 21.6 and throw it into our new list of variables. So we actually don't know what this value is. Our initial velocity in the x, the 12.3 that we solved for, that is going to stay the same because our ball is still launched at the same velocity. It's not changing the launching or what's going on here. Our final velocity in the x will still stay as 12.3 meters per second. Acceleration in the x will still be 0 meters per second squared. And then time, well, again, we have to be careful here. The 1.75 seconds we found previously is the entire time to cover that entire trajectory from where we throw to where the ball is caught. So I can't just plug in 1.75 seconds because it's a time value. It doesn't fit the context of our problem. Now we're number 4. So delta y is now going to be a question. We don't know what delta y is. We knew delta y when we started and ended at the same height, but now we're unsure. I don't know delta y, we're trying to figure that out. Initial velocity in the y direction, again, this doesn't change how we're launching things, it just changes the point we're examining. But initial velocity in the y will still be 8.60 meters per second. We don't really know v1 in the y, kind of unsure there. Acceleration in the y will still be acceleration due to gravity, negative 9.81 meters per second squared. And time, again, we don't know time. Right? We can't use 1.75 because that's the total time to cover our trajectory. Okay? So we can't just throw that in here. Okay, so you'll notice we have our variables listed out. Some of them we've kept, some of them we haven't, because not all of them fit our new point that we're looking at. We're now looking at the highest point on our trajectory, not just when the ball is caught, when it is all the way 21.6 meters away from where we are standing. So, how do we figure this out? Because the problem doesn't give us a whole lot of new information, and it seems like there's a lot of things that are missing. Well, something that we have talked about is this. When an object, we'll just actually stay here, okay? When an object is tossed as a projectile, and it's moving through the air, we have discussed that at the peak of its trajectory, it must stop, even for a moment, in the vertical direction, so that it can begin traveling in the negative direction vertically. So here, at the peak of our trajectory, if we stop vertically, what we mean by that is this. We're still moving horizontally, but we stop moving vertically so that we can begin changing directions and turning around, coming back down toward the ground. So at that point, if we stop vertically, what that means is this. Our final velocity in the y is 0 meters per second. Now you're thinking, hold on, that's not final, that's just at this random point you chose. But remember, we get to choose what points we're looking at. So if I want to call this my final velocity and say I don't really care about what happens after we're here, I'm just looking from start to the top, we can call that our final velocity. Final just means at a point that we choose after the initial. So now that we know this value, well, what we can do is we can solve for delta y. Because we have 3 variables in our y direction, we can find the 4th. So, if we don't know time, looking at our kinematic equation sheet, we should then use equation 5 to solve for delta y. So here we go, equation number 5. V1 in the y direction squared is equal to V0 in the y direction squared plus 2a in the y direction delta y. The equation looks a little bit different. We've just put it in context of the y direction. So V1 in the y direction, we said was 0 meters per second. Since we are at our highest point vertically, our object has stopped momentarily moving up, and it will then begin coming back down. So 0 squared is equal to 8.60 meters per second squared plus 2 multiplied by negative 9.81 meters per second squared times delta y, which is what we are looking for here. Now I'll go through and multiply anything that I can. 0 squared is just going to give me 0. 8.6 squared, I'll plug this in for us, is 73.96 plus 2 times negative 9.81 should give me a negative 19.62 times delta y. And I'll kind of put this in parentheses so we can see delta y is still by itself, which is, well, it's not by itself, but it's separate from the 19.62. It's 19.62 times delta y. So now we want to solve for what is our delta y. Well, 2 things we can do. We can either move over the 73.96 or the 19.62. Doesn't matter which one we choose. I like to stay positive if I can. Pun intended. So we'll add 19.62 times delta y over. Again, the delta y is just a variable, just like x, something we don't know. So now we have 19.62 times delta y is equal to 73.96. So now we can divide by 19.62 on both sides of our equation. So 73.96 divided by 19.62. We end up getting a value for our delta y that is 3.77 meters, which would tell us this is the height when our vertical velocity stops, which means it is by definition the highest point on our trajectory. So if I come back to my variables, I can see that delta y is now 3.77 meters. Which now we have an answer for what is the height of our object at the peak of its trajectory. Now something that might be important for us to understand is how is it different now for our point at the peak? So something else that we could do is, if we wanted to solve for time, we actually could do that. The easiest equation involving time is actually equation 1 on our equation sheet. I'm just going to write that down. And this isn't something we're asked to solve for in the problem, but it is a good way for us to understand what's going on. And V1 is equal to V0, do this in the y direction, plus acceleration in the y direction times time. So V1 in the y is 0 meters per second, V0 is 8.6 meters per second, plus negative 9.81 meters per second squared times t. So if we want to get t by itself, now we have, well, I can just add the negative 9.81 t on both sides of our equation. So we can begin to get t totally by itself. So now we have 9.81 times t is equal to 8.60. We will then divide by 9.81, divide by 9.81. So 8.6 divided by 9.81 gives us about 0.876. So something like this. 0.876 seconds. Now, why do we do that? Do we care? Is it important? Does it even matter? Well, the problem doesn't really ask us for that, but here's what I want you to see. If we come back to the time we found previously, for the entire trajectory, it was 1.75 seconds. Here, our time was, it was here we go. Our time was 0.876. If I take 1.75 and I cut that time in half, I get right about 0.875 seconds. Now you can see why this might be important for us to understand. That in our trajectory here, because it is symmetrical, meaning we start at one height, we end at the same height, and we're looking at the peak on our trajectory, which is right here in the middle, that means our entire time can be cut in half to find our time at the peak. That is another way we can actually go about analyzing the situation. Rather than saying our velocity in the y direction is 0 here, which is true, we could also take our entire time and cut it in half. Now, we can't do that if our trajectory is not symmetrical. Like, for example, if we were to launch from one height and end down at some lower height, or vice versa. If we were to launch from like the ground and throw something out to like hit a window, right? Something like that. And we can only do this if our trajectory is symmetrical, meaning we start and end at the same height vertically. But again, I want us to see these things so that we can understand how these values all fit together in the context of a problem. So overall, hopefully this gives you an idea of how to set up and solve a slightly more challenging projectile motion scenario. If you have questions, don't hesitate to ask them. Overall, good luck with what you're doing, and we hope you do well.